So, we talked yesterday about making trees of things, which is still basically a number line, and one way or another, you end up with smallers on the left and largers on the right. And then it just becomes a process of going, if I'm looking for something, is that the one I'm interested in? If it's not that one, then things that are less than are on the lower side, things that are greater than are on the right-handed side. It's really typical of computer science people to be backwards and draw trees upside down. Don't know why it is. They call them trees, but they're really sort of almost umbrellas. Okay, so don't know why, but we always draw them that way. Okay. In terms of diagrams, you know, if I were to, well, let's just try this. If we write the Java code, what's that thing going to turn into?
Node.
It's going to be a node, but it's specifically, we'll call it a tree node, just to be clear. What kind of information is it going to have in it?
Its value and
the value. So when I draw the thing like this, it's really a link to the actual value. It doesn't have to be a number. That could be in anything, just like it was with any of our other nodes. So that's whatever item we're interested in. Now, what are those things?
branches.
It's there, another tree node for the left and a tree node for the right. Okay? So that's what's going to be in our node class. Okay? If I take that and draw that as a sort of a more traditional diagram, I end up with something that looks like this. We'll put a value in there, call it a string, and I end up with that thing being the left and that thing being the right. Okay? So there's the idea that there's three variables for a tree node. I'm going to break my rule of drawing diagrams for trees, and I'm going to take that line and I'm going to draw it as a vertical line, just because it's a lot easier to see what goes where in this sort of diagram. No mistakes. Okay? So this is left side versus right side node. Okay? If you see me saying draw a logical diagram, all that I'm concerned about really is the values in the tree and the order of them. If I say draw me a memory diagram, I'm more interested in something that looks like this, which is the actual structure of what the code uses underneath. Okay? So logical memory diagram. This one's easier for when we're just trying to see the shape of the thing and the values that are in it. This one's good for when we're talking about how does the code work and how do we actually connect things up. Okay, so that said, we need to make a tree class. And one of the first things that we need is a tree node. And a tree node has an item that we're interested in. So this is tree for E-type things, has an item, and it has a tree node left and a tree node right. I might even call it left side and right side, just to try to give the sense that there's a bunch of stuff somehow under there rather than just a simple thing. The constructor for this is a tree with the item coming in. And we'll just say item equals in item, and we'll make left side null to start with, and right side is null tree node. Okay, so there's the node class for the tree. So what information are we going to need to keep track of for the tree?
Starting node.
The starting node, which is that one, and in official terminology, that's called the root of the tree. Now upside down still.
Trees are upside down.
Apparently, yeah. So this is private tree node.
Devil's bad thing upside down.
Root of the tree. And if we do public tree, we have root starts out as null. Okay. We need some cannon fodder to put into this tree, so I've got the worker class sitting here, our traditional worker. And I've got a driver here, so we can make a tree worker. Workers is a new tree, and we'll add some cannon fodder workers. So there's one. And to start things out, I guess what I should do is choose something that's sort of in the center of the alphabet for the first one, just so that we have some possibility of left and right. The first one is the name, and the next one is their job function or something, but we're only going to worry about the name. By the way, getting things in order alphabetically is something that already makes people's eyes roll, so sometimes numbers is easier rather than letters, but we'll work with letters. Okay, so workers dot, need a name for the method, might as well be add m to the tree. Okay. Now, the way we're going to write this code is we're going to do the smallest, silliest thing first, and then every time we discover that there's a problem, we're going to fix the problem. Okay, so we're not going to worry about what's it going to look like in the future, O or A, or that seems silly. We're just going to do the simplest, most obvious thing and see what happens. Okay, so we'll need an add method in the tree class. So we'll take this item and we'll add it into the tree. What do you have to do to get it into the tree?
Find the topmost branch.
Do the simplest thing first. Where are you going to put it? At the root of the tree. How are you going to get it into the root of the tree?
Set root to the main tree root.
Can't do that because
Because the root isn't a node.
the root is a node, but the item isn't. So this is just like the linked list class. It's a warehouse. You have to put things into boxes in order to store them. So the very first thing that we need to do is always make a new tree node. And dump the thing into the box. And the joy of that is that now we have the left and the right associated with it. Okay. So now what we'll do is we'll dump that thing. Instead of an item, I'm going to call it a node, just so that it's a little bit clearer. we'll dump that thing in. Okay. So the effect of that is I have root, I made a node. The node refers to the M person, and we've got the first one into the tree. Okay? We won't even keep track of the count yet. We'll just leave our tree with just that in it, and we'll go back to the driver, and we'll add somebody else. So there's our next worker now going into the tree. Where do you expect that thing to, actually we should leave some space in there just in case. So instead of adding A, we'll add
G.
F, G, someplace in there. Where do you expect F to hang out, so to speak?
The left side of the tree.
Someplace on the left side of the tree. Okay, so let's go into the add method, and this is where the fun starts. We'll see whether or not we can get the thing into the left side of the tree. The code right now says, take that thing, dump it into a node, and then hook the node up to the root. So if we hook the node up to the root, M is going to go away, and we're just going to be left with A, or F. Okay, so what we've done is we've got this A node that refers to F, and we're trying to get it hooked up. So what's the line that you want to draw?
From the left node.
We want to go from the left side of this thing to A node, which refers to that. So A node needs to be hooked up to the left side. All right? So we make our new node. Well, this code is then there because it's a special case. It's, oh, I'm hooking the first one in. The first one has to go to the root of the tree. Anything thereafter is going to be hooked up someplace down below the root. So it's that same idea of linked list code. The first one you hook up to the start of the chain, or the root of the tree in this case. Every one thereafter goes someplace farther down along the chain in this case. So this is the special case. So if for some reason root happens to be empty, then that's how we would hook it up, and we would get out because that's a special case. Okay. Okay. So now we've eliminated the special case, and we're down to the regular case. The regular case is to say, oh, okay, we'll just assume we hook it up to the left side. So root dot left side equals A node, and then we'd be done. Let's do one more. We'll add S. So we go to add S, and when we add S to the tree, we make a new node. It's not the root, but we're going to hook it up to the left side. Oops. So it could be either left or right side at this point, not always left.
Depends on what it stores.
Depends on what's in the thing that we're trying to place. So really, before we can do that, we need some sort of if statement to decide whether we should put it on the left or whether we should put it on the right. So is it smaller or bigger than the other one? Well, smaller or bigger is what?
Yeah.
Compare to. So the value of the comparison, if we do our old style thing, is to do a node dot compare to, in this case, the root of the tree. Oops. Nodes don't have a compare to. Okay. Let's go down to node, and we'll write public int compare to tree node other. And so now this is going to be return item dot compare to other dot item. So the tree node class isn't going to do anything other than call the compare to for whatever we're storing in the tree. Okay, so that's the same thing we did in the last lab, in lab number 4. But item doesn't have a compare to. So the only way that anybody can ever put anything into this tree is if the items have a compare to, because you have to call it in order to be able to get them in order. Okay? So the tree is the first one that we've encountered because it's ordered where there's a restriction that says you have to have a compare to in the object for this thing to work. Oops. So now the question becomes, how do we force those things to have a compare to? Here's our next bit of Java syntax, is that the problem lies up there, because that could be anything, and now we're saying it's anything as long as it has a compare to. How do you know you've got a compare to? If the, what do you put at the top of the class to wave and say, you don't say implements compare to, you say implements comparable. Okay? So we have to say that those E things must implement comparable, and that's, the syntax for that is extends comparable for E-type things. Lovely, but that's just the way it is. Okay? So there, anything that says it extends comparable, which means it has a compare to. Okay? And we'll just go down and see what happened to there. And notice that our error now went away, because now those things that are in the node are E-type things, and by definition they must have a compare to play this game. And so now look what happened in the driver. All of a sudden we get the warning when we try to use this thing that says, no, workers don't have a compare to in them. So let's go look at worker. And sure enough, my worker doesn't say anything about comparable, so there's no way of being able to put it into the tree, no way of organizing those things. So we have to say worker implements comparable for worker specifically, and we have to add in the compare to, and the compare to can return, we'll just use the first names, so that's, change this to other, so that's return first name dot string compare to other dot first name. Okay? And so now the driver is happy. That error's gone away because workers have a compare to, force that thing to happen. Okay? So that's how you force things to have the methods that you want from the interfaces that you want, is you add extends whatever onto there. And you can extend more than one thing also, so you can force the objects that you're getting to have particular things, particular methods, in order for them to work properly for whatever you're trying to do. Okay, so now that we've gotten that taken care of, we can say, well, the comparison, we'll do the comparison, and then if the comparison is less than 0, we would do something. And this is very specifically either or, so this is one case where I'm going to use an else. Okay, so if it was less than, what would you do?
Put it in the left lane.
Root dot left side gets a node, and this one is, we'll take that thing there and we'll put it only for if it's the right side.
You have to change it, do something left side and left side.
Left side, and this one is right side. There we go, thank you. Run source format. And that gives us putting it on the correct side of root. Just for fun, let's go to the driver, and I'm just going to stick in a print line so I've got something to put my debug statement on. We'll run the debugger until we get to there. And we'll see what we've got in our tree. So there's our workers object. It only has the root variable, and if we crack open the root node, the thing that's stored at the root node is M. The left side and the right side both have nodes on them. The left side has somebody, I should have added a toString and it would have shown up properly. Has F, so that's left side is less than the middle. And this is where it gets confusing in the debugger. That's actually the right and left side for F. So we'll go back up and we'll find, close up root's left side and do root's right side has the other worker, nulls on both sides of it, and it's holding on to S. Okay, so we've managed to get the three things hooked up in their proper sides. Well, that was fun. Let's hook up one more. We'll add C, seems like fun. So just to make sure that we've got this right, we've got M here, we've got F there, we've got S there so far. So if we go to hook up C, it should fall down there someplace. Okay. Well, if we go look at the code for the tree, the problem is that this code stays at the root level, and it needs to drop down a level for everything that it needs to do. Okay? Because if we think of the problem, if the root node had F, then we would just hook it up either to the left or the right of F. So this is, if this is any node, not just the root node, then it would be either to the left or the right of that any node. What would be the sneaky thing to do here in coding style?
To operate as if F was a root node.
So if this could be any node, let's take this code and let's just sort of generalize it a bit down below into, oops, I should put that in a method. We'll call it private void add node internal. It's private because nobody else is going to see it. It's working with nodes. I'm just going to stuff that code in here, and what we're given, tree node, it's not really the root, but we'll leave it as root for now. And we're given some sort of item. Okay? So it's exactly the same code, I've just added parameters on it. Okay? So let's go back up to this case. This case is now, well, if it's not the root, then we'll call add node internal, and we'll pass it the root of the tree along with the item. We've already got it in a tree node, so why don't we just pass it the node and change this thing to the node we're supposed to add. Which gets us a little closer. Okay? Except this code is still dealing with the root. So this is not really root, this is any root. I just want to change the name to make it clear that it's not the very top of the tree. So I'm going to refactor, rename, and call it something a little different. Got it. Okay, so now it's clearly not necessarily the root. Got it. What do you think of that? We're getting pretty close. So let's just go over. Add just says, well, if it's the first one, we'll just add one thing in directly. Okay? So that's just like a linked list. That now gives us something to chain on to in the future, because there's guaranteed to be one node in the tree. Okay? Now, if it's anything past the first node, we're just going to call add internal, and say, hey, I want you to place the thing starting at the first item, so that's chain on to somehow the first item, and there's the thing that I want you to put in the tree. So when things go in, you say, well, we don't need that anymore because it's not going to be the root of the tree. We'll shorten it up to this. So we'll do a comparison to see whether or not we need to place it on the left or the right side. If it's the left side, we hook it to the left side, and if it's the right side, we hook it to the right side. Except
There's already something there.
there's already something there. So if we're here and somebody says hook it up, if there's already something there, we can't put it there, we just have to drop down a level. Okay? And then deal with the problem like this where we can eventually hook it up. Okay? So we can only hook it up onto the left side if there's nothing there. So if there is something there, isn't empty, then we need to do something. What would you like to do? In general, trying to hook it up here, there's already something there. What's the general thing that you're trying to do in English?
Move down to the next node.
Move down to the next level and try to attach it on the next level. Well, attaching it on the next level is add internal again on the left side of the tree, which happens to be any root dot left side, and the thing that we're trying to attach is whatever the node is. And then after that, we would be done because it's the special case. Add node internal.
Semicolon.
I'll get it right yet with a semicolon. And not only that, but because it's symmetrical, if the comparison were greater than 0, then we would do the same thing here. Since I said it, I'll put in a comment. Well, we'll get to that in a second. So this is drop down a level and add it on to the right side instead. So this is call somebody else and get them to do the same work with this node one level deeper, which is the same sort of thing that we did with the recursive version of define beer. Okay? Exactly the same trick. I'm just going to make that a little more obvious. Okay? So there's the code, and notice that I left the else's in because I wanted this thing to try to keep the symmetry. Okay, so that's why the else's are there. So when I go to hook something in, it either goes on the left or it goes on the right. Okay, if it goes on the left, if there's already something there, then the regular case is, oh, we'll just hook it up to the left side. The special case is, uh-oh, there's already something there. I guess we need to drop down a level and get somebody else in this smaller portion of the game to try to hook it left or right of the thing that's one level deeper. Okay. Somebody asked really quickly about what do you do for the case of equals? What happens if I try to put another F in here?
You already have one.
Already have one. I can't place it down below because that's only for things that are smaller. I can't place it for things that are there.
You have to overwrite, or just not do it.
Your choices are, there's three choices. There's overwrite it, thinking it's an update. There's not do it, because there's something already there. Or the other option would be to count it, to say, well, it's identical, so if you try to place it in, we'll just count the number of times it goes in there. Okay? The one that we're going to use is reject it, because the rejection of just throwing away something that's already there will turn out to be an extremely useful property, and I'm not going to tell you why yet. Okay? So for now, we'll just reject it. You could ignore it if, so we'll do it this way, if the comparison is exactly 0, then we'll just quietly ignore it. Say, nope, it's already there, can't have duplicates. Equals says it's the same. Won't even bother replacing it because it's the same. So you can't update the thing that's in the tree. What if you really wanted to update it? How would you update it? Well, if it was by last name, then the tree would be, the comparison would be, it would just be a bigger tree, right? Because you could then have people who had the same first names and last names, and they would still be sorted, but they would still be unique. Okay? But if you had things that were identical for whatever reason, your only choice would be to remove it and re-add it if you really wanted it. Well, removing is going to present a problem that we'll talk about later.
Cut the guts out and swap the guts.
Yeah, there's ways that you could do it. We'll talk about what's easiest and what works. But notice that this is an example where the recursion is really, really useful, because all I've done is I've just put the blinders on and said, if I get it to work right for my level, those are the only possibilities. I'll just trust that if I hand this node off to somebody else at a lower level, they've got the same set of instructions. If it worked for me for all of the cases, it will just magically work for all of them for all of the cases. Okay? So you don't have to concentrate too much on, gee, let me draw things out and see whether or not they work. That's all of the code, and it's pretty obvious. And with that, we're done for the day.